So let's learn about exponents. Well, first, what's a quicker way to count numbers? Well, if I have two over here and I have three more over here, I've learned in elementary school and even before in some cases that I could just say 2 plus 3 equals 5. There's some that would count from 1 to 5, but that's slower. Why does efficiency matter? Well, I guess it always does. Well, what's a quicker way to express repeated addition? Well, some people would say 2 plus 2 plus 2 plus 2, but some others would say that this is just 2 times 4. It saves space, and if you memorize what 2 times 4 is, that answer being 8, you realize that multiplying 2 by 4 is faster than adding 2 over and over and over. Well, in this case, we're asking what's a quick way to express repeated multiplication? And this is the purpose of exponents. So I look at the first one and I see 2 times 2 times 2 times 2. And what we're going to learn now is that instead of writing 2 4 times, I could write a big 2 and a little 4 up in the upper right hand corner. And that means that 2 is being used as a factor 4 times. And that's called 2 to the 4th. And this is called a power. And this 4 is an exponent. And the 2 is a base. So if I did it again, I have 5 times 5 times 5. Well, that's really just 5 to the 3rd power. If I see 3 multiplied twice, I can write 3 with a little 2, and that means 3 to the 2nd power. So now it saves us space when we learn how to write powers, which involve exponents. So what is the exponent when there is none? So I have a 5 here. Well, if you look back at all these other examples, we saw that 2 to the 4th meant 2 times 2 times 2 times 2. 4 2's being multiplied. 5 to the 3rd means 5 times 5 times 5. 3 5s all being multiplied together. 3 to the 2nd meant 3 times 3. 2 3's being multiplied together. So when there is no exponent, then all that means is that there's only one 5 there. So this is 5 to the 1st power. So then in the next case, 2, that would just mean 2 to the 1st power. So obviously then, whenever there is no exponent, the exponent is just 1. So 3 to the 1st power, 12 to the 1st power. When there is no exponent, the exponent is just the 1. So how do you read a power? We touched on this a little bit already, but just as repeated addition can be represented as a multiplication problem, repeated multiplication can be represented as a power. A power has 2 elements, the base and the exponent. So, as we saw before, 2 times 2 times 2 times 2 becomes 2 to the 4th. The entire thing is called a power. It is made of a base, which is the bigger number that's being multiplied over and over, or the number that's being used as a factor, and it's made of an exponent, which is a little number in the upper right-hand corner that tells you how many times to use the base. So again, because this 4 is there, a small 4 in the upper right-hand corner, it says there should be 1, 2, 3, 4s, 4 2's being multiplied together. The base of a power is the factor that is multiplied repeatedly in the power. And the exponent of the power is the number of times the base is used as a factor. So now we want to identify the base and exponent in each power. We're also going to expand the powers and then write each power in words. I'll do the first one and then you'll do the second. So here's 7 to the 5th power. 7 to the 5th power. Just like how the larger number over here is the base, the larger number here is 7. So 7 is the base. And the exponent is the small number in the upper right hand corner. That's the exponent. So the whole thing altogether is called a power. But then we want to expand the powers, meaning instead of 7 to the 5th, what does this really mean? It really means 7 times 7 times 7 times 7 times 7. 1, 2, 3, 4, 5 sevens all being multiplied. 7 to the 5th power is 7 being multiplied 5 times. So now we want to write it in words. That is just 7 to the 5th power. All right. So 7 to the 5th power, very easy to see. 5 sevens are being multiplied, or 7 is being multiplied 5 times. It's not interchangeable. 7 is being multiplied 5 times. So what about 4 with an 8 in the upper right hand corner? You go ahead and take a second and try that out for yourself. So hopefully you recognized that again, the larger number is the base. So the base is going to be 4. The smaller number is the exponent. And so the exponent tells you how many times to use the base as a factor. So this means that 4 should be multiplied 8 times. So if I expand this out, this would just be 1, 2, 3, 4, 5, 6, 7, 8. That is the expanded form. So what about in word form? Well, we've already established that this is 4 to the power of 8. So all I have to do is write 4 to the 8th power. And that's it. So now let's evaluate the following powers. And to evaluate the following powers basically just means to understand what the power represents, write it out the way that it's supposed to be represented, and then actually do the math. Okay? So 2 to the 4th. 2 to the 4th means that 2 is being used as a factor 4 times. So that's 2, 2, 2, 2. 1, 2, 3, 4 times. That's all it means. What would it mean to evaluate it? It just means to multiply the 4 2's. So I'll do these 2 2's first. 2 times 2 is 4. These 2 2's, 2 times 2 is again 4. 4 times 4. 4 times 4 is 16. I could have also went from side to side and just say 2 times 2 is 4, times 2 is 8, times 2 is 16. It's the same result. Let's try 5 to the 3rd. Well, what is 5 to the 3rd? That means 5 is used as a factor 3 times. So 1, 2, 3, and then I'm just going to multiply 5 times 5 times 5. So 5 times 5 gives me 25. I bring down my other 5 since it doesn't have anything to be multiplied with. And 25 times 5 is 125. So 5 to the 3rd is 125. It's really that straightforward. So why don't you try 3 to the 2nd and 7 to the 1st on your own, and then you'll continue after you try those out. So hopefully you, in doing 3 to the second, realize that this means that 3, being the base, is being used as a factor 2 times. So 1, 2, that's it. 3 times 3 is just 9. 7 to the first means that 7 is being used as a factor 1 time. That means that 7 is just there 1 time. And there's nothing to multiply it with, so the answer is just 7. So that's evaluating powers. So let's look at some no math powers. These are some powers that, as you just saw with the last example with 7 to the first, if you understand these rules, you actually don't have to do any math because you can go straight to the answer. So the first thing that we're going to learn about are bases raised to the first power. So how do you raise a base to the first power? Well, you really just realize that since 2 to the first power means that 2 is only used 1 time, you just write 2 once. So 3 to the first power is 3. 5 to the first power is 5. 17 to the first power is 17. 105 to the first power is 105. X to the first power is just x. Whatever the base is, any base raised to the first power is simply that base. So no matter what the base is, if the exponent is 1, that means it's being raised to the first power. You simply just rewrite the base. The second no math power are base 1 powers. So if I have 1 and it's raised to the second power, well, what does that mean? That just means that it's 1 used as a factor twice. So 1 times 1 is really just what? It's just 1. So 1 to the second power is 1, but is that any different if it's 1 to the fifth power? Well, let's see. That's 1 used as a factor 5 times. So 1, 2, 3, 4, 5. Well, 1 times 1 times 1 times 1 times 1 is still just 1. So if I pay attention to the rule, I don't have to actually do any math when 1 is raised to a power. I just know that the answer every time will be 1. So 1 to the 12th power should be what? Just 1. 1 to the 100th power will still be 1. So if you learn that rule, again, if you have 1 raised to any power, the answer is just 1. Another no math power is base when you're dealing with base 0 powers. When the base is 0, well, what is the answer? Again, same idea. If 0 is being used as a factor twice, in other words, being multiplied twice, that's 0 times 0. But what is 0 times 0? That's just 0. So 0 to the fifth power is 0 times 0, 3, 4, 5. But 0 times 0 times 0 times 0 times 0 is still 0. So then what is 0 to the 12th power? It's just 0. What is 0 to the 100th power? It's just 0 again. So no need to do math if you see that 0 is being raised to any power, because no matter how many times you multiply by 0, the answer is still 0. Now, what about things raised to the 0 power, or to the power of 0? Well, this is a little different. So this is a rule that you kind of just, for now, have to just learn it. So 2 to the 0 power, in the larger context, the answer can't be 0, because that would mean that your answer, when it's raised to the 0 power, is going to essentially eliminate whatever other math you're trying to do. So for the purpose of multiplication, we have to know that 2 to the 0 power is just 1. And again, the logic behind this, there's more I could explain, but for just learning purposes right now, 2 to the 0 power is 1. Because really, any base raised to the 0 power is 1. So 3 to the 0 power is 1. 5 to the 0 power is 1. 17 to the 0 power is 1. 105 to the 0 power is 1. Even x raised to the 0 power is going to be 1. So that's a rule that you kind of just have to learn it and run with it. It makes your math easier, so why argue with it anyway? Any base raised to the 0 power is 1. If that exponent is a 0, the answer is going to be 1. Now, you can also take powers with the same base and multiply those. So powers with the same base can be multiplied. But if you pay attention to what's actually happening, you can learn a rule that makes this process go faster. So if I did 2 to the third times 2 to the second based on what I currently know, that would be 2 to the third is 2 times 2 times 2. That's 2 to the third. In fact, let's just write it underneath. So we start off with 2 to the third and multiply it by 2 to the second. That means 2 to the third is 2, 1, 2, and 3. That's 2 to the third. Sorry, I wrote that wrong. That's 1, 2, 3. We also know that it's being multiplied by 2 to the second, which is 2 times 2. Well, if you look at what we've done now, we've now made a new repeated multiplication problem. So I see 1, 2, 3, 4, 5 2's all being multiplied together. And we learned earlier that that would just be represented as 2 to the fifth. So what I'm going to do now is say, well, I had 3 2's being multiplied. I had 2 more 2's being multiplied together, and that ended up being 2 to the fifth. Well, if I take this 3 and this 2 and add those together, that would have been 2 to the fifth as well. So there's a rule that says that if you're multiplying two powers that have the same base, the 2 and the 2, I can just add the exponents and that'll save me a lot of time. So look at how that works now. 5 times 5 to the third. Well, we learned earlier that if there is no exponent, this exponent is really a 1. So that's 5 to the first times 5 to the third. We also just learned that if you have two bases with the same, two powers with the same base, I can just add the exponents. So this is 5 to the 1 plus 3. And since 1 plus 3 is 4, this is just 5 to the fourth. I could have done it longhand, but I don't need to waste that time because this rule is an efficient rule that works consistently. Let's try it again with 3 to the fourth times 3. Again, if I don't have an exponent with this 3, that means that that's just 1, 3 to the first power. So now I have 3 to the fourth times 3 to the first. The bases are the same. If I'm multiplying, I can add the exponents. So that's 3 to the 4 plus 1. So 3 to the 4 plus 1 would just be 3 to the fifth power. So we're not concerned right now with finding out what the final numerical answers are, but we should know that if we're multiplying powers with the same base, I can add the exponents, and that's another way to express these expressions. So x to the second times x. Well, again, there's no exponent here, so this becomes a 1. So x to the second times x is x to the 2 plus 1. And that just means it's x to the third. And again, it doesn't matter what it means beyond that, but we do know that when you have powers with the same base, you can multiply them by just adding the exponents. But powers can also be raised to a power. So how would you go about doing that? Well, if I have 4 to the third, and that whole thing is raised to the second power. But if you think about it, let's just look at the first one. This is 4 to the third, and it's the exponent still tells you how many times to use the base as an exponent. So in this case, my base is 4 to the third, and it's being used as a factor 2 times. So that's 4 to the third times 4 to the third. So if that's 4 to the third times 4 to the third, now it takes us back to the rule that we just learned. That says since the bases are the same, I can just add the exponent. So that's 4 to the 3 plus 3. But then somebody might look and say, well, 3 plus 3 is the same as 3 times 2. And you'd be right. So another way that you could have done this from the beginning, so this is 4 to the 6th. But another way you could have done this from the beginning is you could have simply said that this is the same as 4 to the 3 times 2. So I could have said, if I come over here, 4 to the 3 times 2. And that would have also given me 4 to the 6th, one step faster. So what's the rule? If you have a power and it's raised to another exponent, then all you have to do is just multiply the exponents. So 4 to the 3 times 2 gives you 4 to the 6th. Look at it again. 3 to the second raised to the fourth power is just 3 to the 2 times 4. And that's just 3 to the 8th. And you can also tell because the little exponent on the inside and the little exponent on the outside are separated by parentheses. And normally, when you have one number inside and one number outside, that's multiplication. So 5 to the 6th raised to the third power can be 5 to the 6th times 3. And that's just 5 to the 18th. And 2 to the 5th raised to the 6th power is 2 to the 5 times 6. And that's just going to be 2 to the 30th. Now, we're not exactly concerned about the actual end product. That's not our concern. We're just focusing ourselves on learning this rule that if I have a power and it's raised to an exponent, if I have another exponent outside and there's nothing else attached to it other than just that exponent, you can save a lot of time by just multiplying these two powers or multiplying these two exponents. So what about these? Because these are some somewhat special situations in some cases. So I have 5 times 7, right? So you don't see any exponents, so that's just 5 times 7. And we know that that answer is 35 because I wanted to confirm for you that when you have two bases, and again, this is a 1 and that's a 1, you have two bases, 5 times 7, I can just multiply 5 times 7. There's nothing special about this. In the same way, 3 times 2 is just 6. So when I have one number inside parentheses, another number outside parentheses, if they're both large bases, then I can just multiply them. I want you to not be confused by what you're going to see in the future. So 8 to the second. So the 8 is in parentheses, but there's a small 2 outside the parentheses. So this goes back to the rule that we just learned. If this is really 8 to the first power, then I'm not going to multiply 8 by 2 because this is a power being raised to a power. So this is 8 to the 1 times 2, which is really just 8 to the second power. So that's really all you need to understand. And if you want to go further, you can say that 8 to the second power in this case, yes, it's 64. But the biggest thing to understand was that if you had the whole number inside parentheses and then you have a exponent outside, you're going to make sure you understand that the missing number is a missing exponent is a 1, and you multiply it by the number outside, which really just means raised to the second power. So now we take all that into account and look at this problem here. So we have 4 times 3 to the second power. Well, as it stands right now, I should not believe that I can multiply 4 by 3 because I should know that the first thing that makes the most sense is to take care of what's inside these parentheses first. So since there's no other exponents to work with and no common bases, then you should just be doing 3 to the second power first. So this is going to be rewritten as 4 times, and what is 3 to the second power? That's really 3 times 3. You're not actually obligated to rewrite 3 times 3, but it'll help you just to see what's happening. And this means that that's 4 times 9, and 4 times 9 is therefore 36. Again, I'm not obligated to go from left to right. I'm obligated to work with what's in the parentheses first. So 3 to the second is really 3 times 3. That becomes 9. 4 times 9 gives you 36. Because again, when I looked at these problems before, when I have two bases separated by parentheses, that means multiplication. 2 times 1 to the 4th power. Well, again, I learned earlier that I have to do the parentheses first. And since 1 is raised to the 4th power, we learned earlier that any time that 1 is raised to any power, that's just 1. So what does this mean? This is really just 2 times 1. And what is 2 times 1? That's 2. So something that looks complex is really actually pretty easy. Finally, I have 7 times 2 to the 3rd power. Again, I'm going to take care of my exponents first, or my power first. So this is going to be 7 times 2 to the 3rd, which is 2 times 2 times 2. So if that's the case, this is really just 7 times 8, and 7 times 8 is 56. And in reality, we could have just kept on holding to the idea that if you know 2 times 2 times 2 in your head, you could have went straight to 7 times 8, because this is about being efficient. The whole purpose of learning these rules is to be efficient. So that's what I wanted you to have a firm understanding on. So that's it. As you can see, the rules are not difficult to understand. If I was to give a quick recap from the beginning, again, we know that addition is a faster way to count. We know that multiplication is a faster way to add the same numbers over and over. So exponents are a faster way to multiply over and over. The base is the big number that's being used as a factor over and over. The exponent is the smaller number that tells you how many times to use the base. So when there is no exponent, you just make it a 1. When you're asked to evaluate a power, that means to go ahead and write it out the way that you know that the exponent tells you to write it out, and then you just multiply like normal. There were some special rules that says that if something is raised to the 1st power, you basically just keep the base. When 1 is raised to any power, you basically just know that the answer is going to be 1. When you have problems where the base is 0, the answer is going to be 0. When you have numbers or bases raised to the 0 power or to the power of 0, the answer is also going to be 1. You can multiply powers that have the same base by adding the exponents. And you can raise a power to a power by multiplying those exponents and basically keeping the base. In certain special situations where you have a power inside the parentheses, you should, if there is something outside the parentheses, deal with what's in the parentheses first, and then you can multiply like normal. So those are all the things that you are supposed to know about exponents up to this point. So hopefully you were able to get a grasp of this. If there's any issues or questions, then reach out. But let's get this done.